Logarithmic functions as inverses is the name of the section. Write down that definition of a logarithm. If, and make sure you read this correctly, if we have log base A, the little number is the base number, log base A of B equal to x, then you can convert that to exponential form. A to the x equals B. We've got a couple of examples down below where we go from log form to exponential and exponential to log. If you understand that, then you understand the definition of a logarithm. Alright, the first one. Write this log base 3 of 9 equal to 2 in exponential form. You always take the base number, raise it to this power on the other side of the equal, and it should equal this. So in exponential form it would be 3 squared equals 9, which is a true statement. So if it's true over here, then this has to be a true logarithm. Okay? Another one right here in red, if I give you log base 5 of 125 equals 3, you need to be able to go to 5 cubed equals 125. Does that make sense? Does everybody understand how to go from log form to exponential form? I think it's easier to go from log to exponential than it is to go from exponential to log. But down here below, if I give you 4 cubed equals 64, you should be able to write that as log base 4 of 64 equals 3. Okay? Same thing over here. If I give you 7 to the 4th equals 2,401, which it does, you need to be able to write it as log base 7 of 2,401 equal to 4. Okay? So just make sure you understand from the definition that you take this number, raise it to that power, set it equal to that number. Okay? Any questions? All right. Next. So we had to use the definition to evaluate logarithms. Right now we can't use the calculator. On your calculator, the base number, you can't type in a base number on your calculator. You have to use the change of base formula, which we're not going to do yet. The base number is understood to be 10 on your calculator at all times. So in this case, if I give you what's in black, this won't be given to you in blue. They give you evaluate log base 8 of 16. So what I did, I just set it equal to x, made an equation out of it so I can evaluate it or solve the equation. Using our definition, we know that 8 to the x, change it to exponential form, 8 to the x must equal 16. Then from there, what common base do 8 and 16 have? 2. Because 8 is 2 cubed, 16 is 2 to the 4th. Once you get the base numbers to be the same, you can set the exponents equal. Question?
Why did you get 2?
Because 8 is 2 cubed. 16 is 2 to the 4th. Right? Okay, once the bases are the same, set the exponents equal and solve for x. Does that make sense? Yes.
Is there an easier way to figure that out if you have two numbers, what they share in common as the power?
No. I would just start with 2. And if 2 doesn't work, go to 3. 3 doesn't work, go to 4.
Okay. Why can't you set the exponents equal to each other? Oh, because 2 and 2 is 1.
Because the bases are the same.
Oh, okay.
Okay. Over here, this one's a little more tricky because we have a fraction, but you do the same. You have log base of 64 of 1/32. Set it equal to a variable, which is x. 64 to the x equals 1/32. I don't want fractions, so I took the reciprocal here, which made my exponent a -1. Y'all remember that? From here to here? Okay, so get rid of the fraction. Now, the common base here is also 2. If there's a larger one, then use it, but there's not. 64 is 2 to the 6th. So 6 times x is 6x. 32 is 2 to the 5th. 5 times -1 is -5. So again, once the bases are the same, set the exponents equal to each other and solve for x. Does that make sense? Okay? So basically we're using our definition of a logarithm, getting the same bases, and then solving. Does everybody have that down? Alright. Graph. The graphs of logarithms, just like we were talking about a minute ago, this is the graph, the red is the graph of an exponential growth, right?
Yeah.
And the main point we focused on for exponential growth or decay was 0, 1. And it's a reflection for logarithm. The main point we're going to focus on here is what? 1, 0. And this is why. Change this first to exponential form. Even though the y is on this side, you should still be able to tell that this converts to 2 to the y equals x. Everybody see that? Okay, take the base number, raise it to that power, set it equal to that. Now what I would do when I do the table, I will give you the y values in this case. And you have to figure out what x is. Okay, because y is a power. It wouldn't do me any good to give you x and you find y. Yes?
From the 2 to the y power equals x, is that the same definition as the log?
Yes. Okay, so I gave you -1, 0, 1, and 2. If y is -1, what's x?
1/2.
1/2, because 2 to the -1, you got to take the reciprocal, which is 1/2. 2 to the 0 is 1. 2 to the 1 is 2, and 2 to the second is 4. So I plotted all these points. 1/2 -1 is here. 1, 0, 2, 1, and 4, 2. And there is your curve. That curve is an inverse of a exponential curve. For them to be inverses, they have to be a reflection, y'all remember this? Along this line. Everybody see the reflection? What is that line? What's the equation of that line?
Z is x.
Y equals
Y
x.
equals x.
So linear function, and it has to be y equals x for them to be inverses of each other. Now, we don't have a horizontal asymptote. For the exponential, we had a horizontal asymptote. What type of asymptote do I have in this case?
Vertical.
Vertical, and what is it?
X equals
X equals 0. Okay?
How did you graph the red? What did you do with the red line?
The red is just, we went back and just graphed an exponential to show you how it compared to a logarithmic.
So
This
you,
goes back to section 1,
oh, so you just graphed.
graphing exponential function. Yeah, I just put it up there just so you can compare the two.
Oh,
Okay?
could you let me write the graph?
Yeah, I'll come back to it.
Okay.
Alright, and here, same thing. I'm not too concerned about the actual points. If you are, you can make a table of values. Here, I just care about the translation. And the point that we want to translate from the parent function was 1, 0. So this number right here is going to tell me to move it right 2. And that number is going to tell me to move it up 3. Okay? Now if I move a point 2 units to the right, I've also got to move the vertical asymptote 2 units to the right, which I did here. And there's your curve. That's all I need to see. This curve, this point, and the vertical
So you don't have to
asymptote.
worry about anything besides what's in parentheses and what's out.
Correct. Okay? Does that make sense? The translations.
Wait,
Now the one before that we did, I do need to see the table there. And I will give you, like I said, I will give you the y values. So if it
Is
doesn't
it
involve
best to
a,
use-
if it doesn't involve a translation, then I do need to see the table of values. What?
Is that -1, 0, 1, and 2 the best ones to use?
For that, yes. If it were a fraction less than 1, then I would go -2, -1, 0, 1. Just like we did when we were doing growths and decays.